Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of vegetables. Um, so I'm not going to use the test CSV because we don't have price attached for it, and I want to get a sense of how the model is performing. So we're going to use vegetablemarket.csv, which basically contains a bunch of different, well actually just 6 different features about different vegetables. Now we do have duplicate vegetables in here, but it's a different occurrences of each vegetable. At the end we have the price per kilogram, and we're going to try to predict this with regression models based on the other 6 features. So let's hop into the notebook. I'm going to be using NumPy and pandas for working with the data, and then for pre-processing we'll use the train test split function and standard scaler from sklearn. Then our models can be a whole bunch of different models. We have some standard models, 3 linear regression models. These are just different types of regularization that are applied to linear regression. Then we have the k-nearest neighbors algorithm, a neural network, 2 support vector machines, one with a linear kernel, one with a nonlinear kernel, a decision tree, and then these are all of our ensemble models. I believe they are all tree-based. So we'll see how this goes. Let's go and import all of that, and I can get the file path to the CSV file up here, copy file path, and I'll just load it in with pandas.readcsv, paste in the file path, and we will take a look. Alright, so it's a very simple data set. We do have to encode a bunch of these columns. We can get a little more information about the dataset with data.info. And you can see we have 5 object columns. There are only 2 integer columns, one of which we are trying to predict, which is the price per kilogram. We also can see we have no null values, at least not encoded as NA. So let's start pre-processing. So as usual, I'm going to create a function called pre-process inputs. That's basically going to take in a data frame. For now, all it will do is create a copy of the data frame, df.copy, and return the data frame. So we can use this to modify a fresh version of the original dataset each time. So I'll store the modified version in X, and we will pass in data to our function, and then see the results here. And now anytime we want to make a change, we can see it on a fresh version. Okay, so we have 2 integer columns, and they're already ready to go, but the rest of the dataset is not. So we're going to need to employ various encoding schemes depending on what type of categorical features these are. So we can get a sense of that by taking a dictionary that maps each column in X to the length of unique values in that column. So we'll take x subcolumn.unique and then take the length of that, and we'll do this for every column in x.columns. And we can see now the number of unique values in each column. And the reason I'm doing this is for this. We want to see if any of the categoricals have 2 values. If they have 2 values, we know we need to do binary encoding. Binary encoding is very simple. That's this column here with yes and no. Basically, binary encoding is just send one value to 1 and the other value to 0. So let's do that first. So binary encoding. Basically, we're just going to take this column name. We're going to take the column and use .replace on it. And replace allows you to specify a dictionary with a mapping of values inside. So we know there's 2 values here, we can see it there. And that's yes and no. You can see them here. We can send no to 0 and yes to 1. However, I'd like to point out that it doesn't really matter which you choose, as long as you send 1 to 0 and the other to 1. So we'll send no to 0 and yes to 1. And we'll store the result back in the original column. So now if I run this down here, you can see we have 0s and 1s where we originally had no's and yeses. So that has been taken care of. let me actually, instead of seeing all of the columns, I'm just going to see the object columns, or the categorical columns. So for that I can use select dtypes, specify a data type to look at, and then just get the columns with an object data type here. So we have vegetable, season, month, and vegetable condition. And these all have more than 2 values. So binary encoding won't work. We have to, in order to know exactly what kind of encoding we should take a closer look at the values in each column. So we can do this with list, or we can just look here, but list is nice because we can actually see the values as lists. As long as you don't have too many values, this is nice visualization of what's inside. And you can see, alright, so right here we have unique vegetables, and there's not too many of them. And these have no ordering between the values. So when you have a categorical feature with no ordering between the values, we're going to want to one-hot encode that feature. So for that we can use pandas.getDummies. Well, for example, the vegetable column, if we get the dummies for x sub vegetable, you'll see each vegetable, unique vegetable, gets its own column, and a 1 will represent the original value of an example. So here we have a 1 in the potato column for example 0, and if we look up here, that's because for example 0 we had a potato value for vegetable. And so this is a way to encode nominal features, which are features with more than 2 values whose values do not take in ordering, as long as you don't have too many values. Because as the number of unique values goes up, so does the number of columns, and if you have too many columns, it can really slow down the model's performance. But for our purposes, this will be just fine. It can also cause the model to overfit, I will say, if you have too many features. Okay, so the other ones. This is interesting. Okay, so season. Some might argue that season could be an ordinal feature, which basically ordinal feature is when the values have an ordering, right? But you can see here that we have monsoon season, and there's not really a good way to specify the way you ordinal encode is send each one to an integer, such that the integers are in order, so the model can see it as a continuous variable. However, it would be difficult to assign monsoon to a proper integer or float, because we can't really say for sure where this lies. I mean, it may be up for the exact position of the float would be up for debate. So I think one-hot encoding is still the right move for season. However, for month, these are all fairly evenly spaced values. We know January, February, March, April, May are all very evenly spaced, so we know how to space them. So ordinal encoding is a perfect approach for the months. I would like to point out we have a missing value here, that it was encoded as a space, so we're going to have to deal with that. Now we will do an ordinal encoding using the toDateTime function of pandas, which makes it a lot easier for us if we are dealing with dates like this. Alright, so then we have this last one, vegetable condition. There is no ordering between these. Technically you could say that scrap comes first, then there's average, then there's fresh, but we don't know how to position those along an ordinal feature. We don't know the spacing of them. So we're going to one-hot encode this as well. And we can notice here that there is a misspelling of scrap, so I'm gonna fix this up before we do anything. Clean vegetable condition column. We can do that similar to how we did down here. We take the vegetable condition column and call it replace, and we pass in the correction. We want to map scarp to scrap, and we'll store the result in the original column. Now if you look here, you can see we just have 3 values. Okay, so let us now do the date encoding. So let's worry about this month. Before we do the one-hot, let's worry about this month column with a date encoding. So the reason I'm calling it date encoding is because we can use this nice function from pandas, toDateTime, that will take in a column. We can actually just take in a value, let's say Jan, pass it in here, and you can see, well, it doesn't recognize the format, so we do want to specify the format in here, and the code for the month abbreviations is %B. And you can see that actually will give us a timestamp. Now the year doesn't really matter, the hours doesn't matter, because the only information it got was January. But if we were to change this to April, you can see the month changes. And this is useful because now we can type .month to get back the month as an integer. And that's very nice because this will do the ordinal encoding for us. Now I would like to point out that we can do this sort of thing for the whole column at once. If we pass in the column, which is x sub month, oh, okay, so actually there's an issue. We have some, because there is, okay, there are some problems because these aren't encoded properly. In this case, because it's not really encoded properly, because we have some abbreviations and some full names of months, toDateTime might have some errors. If we do want to deal with errors, you can pass in the errors argument. One option here is to raise an error, which is what it does by default. Just brings up this error. Another one is to ignore the errors, which will convert all the ones that it can do well, and then leave all the rest. And in this case, it seems like it's not actually... yeah, it doesn't seem like it's doing so well. Let me try this. I want to see if we can get back the month. Alright, and it's not working. So, yeah. It's not liking this encoding. So, the last thing you can do is coerce, which would actually... Well, that one actually worked. You can see it. Now it actually did apply it, but when it finds an error, it will turn it into a not a time value, which is considered a missing value, which we can then fill later. So if we now try to apply x becomes x.month to each one of these, you'll see we have a month value for each one. And you can count up how many missing values we have with isNA.sum, and there's 20 missing values in there. Now, I think because of the encoding, it probably found more missing values than there actually should be. So I'm going to apply a different approach. I'm actually going to grab this list, and I'm going to manually map the values. So this could be more ordinal encoding because I'm not using the toDateTime. Basically, we'll turn this into a dictionary, and we'll use the replace thing that we did use earlier. So let's bring this all the way to the side, indent this over, and now I'm going to go through and apply these mappings. So January will become 0. We could do 1, it doesn't really matter. Yeah, I might as well do 1. It's not going to matter because we're going to scale the data later. April's 4, July is 6th, no, 7th, September is 9, October is 10, December is 12, May is 5th, August is 8th, June is 6th. This one we're going to map to a missing value, not a number, and March will be 3. And we don't really have to order it. I mean, actually, like, place these in the proper order because we have the mapping specified explicitly. And we know these are all the values in there because we saw it down here. So what we can do now is take the month column and call .replace and pass in this dictionary. So we'll grab this, pass it in here. Yeah, I'll put it like this. Alright, and then I'll just indent this up one. There we go. I want to store the result in month after we're done. And now let's take a look. not the dummies. We're going to look at X. Alright, and our month has been encoded. So let's count up the missing values in month. And we now have only 3 missing values. So before it found 20 missing values, and that was due to the improper encoding of the months. But here you can see the months have only 3 missing values. So now let's actually fill those missing values. Fill missing month values we'll use the column mode. Now, the reason we use mode and not mean is because we want to we want to understand what this feature means. It doesn't make sense to have 1.5 months. Technically, the model wouldn't see a problem with it, but we still want to sort of keep, if we're imputing values, we want them to be as realistic as possible. So mode is the right move here, in my opinion. Let's take, basically we just take month and use the fill_na function, and we pass in the value we'd like to fill the missing values with. In this case, it will be the mode of the column. So .mode, and then the mode actually returns a series, so we want to get the first value of that series, which is the actual numeric mode, using sub0. And we'll store the result back in month. Now if we run this and we look down here, you can see we have no more missing values in any columns. Alright, and in addition, our list of uniques in the object columns has now been cleaned up. We just have to one-hot encode the remaining columns. So let's do that. We're going to create a function called one-hot encode. And this is going to take in a data frame and a column. And it will start by creating a copy of the data frame so that we're not modifying the original version. And then we are going to create the dummies. So I showed you the dummies before. I deleted them, but basically just one-hot vectors for each example for each value in the column. And we'll use getDummies for that, passing in df subcolumn. I guess I'll show you again on the vegetable column. Whoops, it should be X. Here it is. If we use the prefix here, we can actually specify a prefix. Let me just make it the same as the column name, and you'll see now it adds a prefix to the beginning of each column name. And this is useful because we can see where these values are originally coming from. Alright, and I'm going to use that down here. I'm going to specify a prefix will be the same as the column name. Alright, once we have our dummies, we want to concatenate them onto our dataset. For that we can use pandas.concat. We're going to concatenate the original data frame and the new dummies side by side, so axis 1. And then when we're done, we'll just drop the original column from which we created the dummies. And that will do it. So there's our function. Now let's do the final one-hot encoding. So for this, we want to do it for all 3 of these columns. So let's look at that with keys. That's just 3 columns here. We're going to grab that list and say for each column in this list, we'll use our one-hot encode function. We pass in the data frame and the column that we're iterating through. And let's take a look. And here it is. So we now have 29 columns, and all of our one-hot columns are on the end of the data frame. Our original columns are still here, but the data is in fully numeric form, and we know there are no missing values remaining. So we are ready to scale the data and train our model. So scaling, certain models perform better when, much better actually, when all the ranges of values in each column are the same, or very similar. So right now we have all different ranges. These one-hot columns take only values between 0 and 1, 0 or 1 explicitly, whereas this is an integer ranging up into nearly 100. And so we want to make sure that every column has the same range. Now there's many ways to do this. Well, there's a few ways to do this. One would be to constrict the values into explicitly into a range, which would be called a min-max scale. And we can do that with the min-max scaler from sklearn. You could say we could send the minimum to 0 and the maximum to 1, and we'll squish all the other values in between that range. However, this approach is not so good at dealing with outliers. If you have outliers in the data, sometimes the min-max scale can be better than the standard scaling, which is what I'll discuss next, which is what we'll actually be using. The standard scaler will give each column a mean of 0 and a variance of 1. So instead of squishing all the data, it will shift and scale the data for each column so that all the columns have the same mean and the same variance. And I find the standard scaler usually outperforms the min-max scaler, but not in all cases. Sometimes the models perform better with a min-max scaled input. So we'll scale x. Before we do have to split the data. So we're going to split df into x and y, because we don't want to scale y. Y is what we're trying to predict, this price per kilogram. If we scaled this, it wouldn't really mess up the model's predictions on the test set, which we're generating from this data set. But if we it wouldn't work on real data. Like if someone now actually inputs a price per kilogram, it won't work because the model is used to seeing scaled prices. So I mean, I'm actually not sure how it will affect it if we did scale it, but it's not a good idea to scale the target column. So we want to split it first. Y is going to be df sub price per kilogram, so I'll grab that column name. And then x is all the rest of the data. So we'll drop this column from axis 1 and store that in x. After that, we're going to do a train test split. So this will send 70% of the data to the train set and the other 30% to the test set. The actual percentage is up to you, but for this we'll use the train test split function from sklearn. Passing in x and y, we want to split them the same way, and specify a train size. So I'm going to use 70%, which is pretty standard. It gives a nice balance between giving the model enough training examples and also having a representative subset as the test set. However, you can play around with this a little. This will also shuffle the data. So shuffle equals true is on by default, but I'm just leaving it in there. So because we're shuffling, I want to include a random state, which will ensure that the shuffle and therefore the split is always done in the same way when we reproduce the results of this notebook. And this will return 4 new sets of the data: xtrain, xtest, ytrain, and ytest. And these are the 4 sets that I want to return from this function. We can get them down back here. We can get them back down here. And we'll take a look at xtrain. So this no longer has our price per kilogram column. That is being stored in ytrain. And additionally, this is only 70% of the data. So I know this isn't really a lot of data to train on, but we have the data we have. So the indices between these are matching up. The test set will contain the other 30%. Alright, so now we can scale. I'm going to create a standard scaler from sklearn, which, like I said, will give each column a mean of 0 and a variance of 1. We can then fit the scaler to the train set. And we're not fitting to the test set because we want to sort of pretend that we don't have access to the test set while we're doing the pre-processing. So once we've done that, we can transform both the train and test set using scalar.transform. However, this does return a numpy array. So if I run this, you'll see the data's been scaled, but it's not so nice to look at anymore. So I'm going to go back and turn it into a data frame. And because I'm creating a new data frame, I want to specify the index to be the same as it was before, and the column names to be the same as they were before, like so. Then I'm just going to do exactly the same thing for xtest. And now if we return this, you'll see that we have a data frame again, and all of the values have been scaled. So if we look at the means of each column, they're all very close to 0. And if we look at the variances, they're all very close to 1. So the scaler has worked, and we're now ready to train our models. So let's start training. So we're using a whole bunch of models today. These are all of them. And for the sake of time, I'm just going to copy in a dictionary that I wrote, that I created, that's mapping the column name to an actual instance of the model name to the actual instance of the model which we can fit. So we can now just use a loop for name and model in models.items, and the items will just return the key value pairs as tuples, which we can iterate through two at a time. And for each pair name model, we'll fit the model on the train set, and we'll print out a confirmation message with the name, just saying the model was trained. And there we go. You can see all the models were trained. It went very quickly because we have so few training examples. We also don't have too many features, so that speeds up the model performance. The model training. And then our results will just be by iterating through again for name model in models.items. We'll print out the R-squared score of a given model evaluated on the test set. So the R-squared score is a measure of how well the regression model is doing on a set of data, and it basically measures how dispersed the data is around the fit that your model found. So we'll print out the name of the model, followed by R-squared score. And we'll display the R-squared score to 5 decimal places, and format this string using model.score. So for scalar models, the score function will return an R-squared score as long as it's a regression model. So we'll pass in xtest, ytest to see the results. Alright, and here it is. And as you can see, it looks like it's a very interesting set of results. Some of these models really did not do well. Especially the neural network did fairly badly, and the support vector machine with a radial basis function kernel. Now, the linear regression actually did quite well compared to the others. All three of them did fairly well. K-nearest neighbors completely missed. The linear kernel SVM didn't do so well either, but not as bad. And then our tree-based models all did fairly well except for light GBM. So I'm actually not sure why this is so low. It's very low compared to the others. And XGBoost actually wins with a 0.78 R-squared. Now I would like to point out that the number of test examples we have is very low. So when you have such a small set of examples to evaluate the model on, it might not be producing the most accurate results. You might be able to get a better sense using k-fold or something, which will just evaluate on different subsets of the data. For example, if I grab these results, and maybe I'll change the split changing the random state in our train test split, so that a different set of examples goes to the test set. If I run that, and I retrain the models, and then I take a look at the results, you can see they're completely different. So we really can't say which model is doing the best here. However, we can look at what the best R-squared score was, and we can also look at the average R-squared score. So before, we had a 0.78, which was the highest out of, none of these even came close. So that's very interesting. But it does look like these models are doing roughly the same level of bad. None of them are getting, I should point out, the maximum value R-squared score can have is 1, and the lowest value is there's no bound on the lower value. So it can go deep into the negatives. And so these are about 0 for both of our splits. Alright, so results are a bit inconclusive, but it's alright. If you want to take a look at the notebook, maybe you can find some more reliable results. But that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.